Okay, several things. Got some folks in quarantine. Yesterday, I think it was yesterday, you should have gotten an email. And if you're not checking your college emails, that will be to your detriment. So I realize that most people come here, they already have probably more than one email address, but all your college notifications go to your college email address. Okay. And so things that regard financial aid, stuff you need to sign, all that stuff, all that goes there. And well, yesterday there was a notice went out from Dr. Mountjoy. Okay, come on, stop that nonsense. Went out from Dr. Mountjoy saying that there had been a change in the college schedule. That may have happened on Monday or Tuesday night. This is important. October 19th, which is 2 weeks, well, a week and a half from now, was going to be what's called Fall Day. That usually follows our homecoming. And it's a day to recuperate from homecoming activities and everything. So since all those activities are canceled, what they decided to do is to have classes that day. So on October 19th, which is on your calendar, will be an ordinary class day. It is not a day off of school. In exchange for that, Friday, November 20th will be no school. So they swapped 2 days. Friday, November 20th is the Friday before Thanksgiving break. So they did. So what they don't want to do, this was a very wise safety move by the administration. And it's a very good thing. Because what they didn't want is over a long weekend, a bunch of people going home and bringing back grunge from wherever they're at, possibly. That is the biggest worry, is when a lot of people go out of town and converge back in a place, right? So, they swapped those days. So October 19th, we're having class as normal. Friday, November 20th, no class. So basically, you're getting a 1 day early start on Thanksgiving break. Connected to that was something I announced the first day of classes. It's very, very important. And that is the week before finals, the week before Thanksgiving is going to be the final in here, quote unquote final. Remember that? It's going to be an exam over all the material we've covered up to that point. I had previously said, plan on taking that to 19th or 20th. Okay. Now I'm going to do 17th, 18th, or 19th. 17th, 18th, or 19th. 3 days. Okay. Yeah. Go ahead, Alejandro. That should be a Tuesday, Wednesday, or Thursday. 17th, 18th, and 19th. Yeah, good. Thank you for verifying that. So the 20th, you're gone. So 17th, 18th, or 19th. I know that some people before breaks, you think COVID's bad? Oh, you got to see the exam flu. Before breaks, under no circumstances am I giving this exam after Thanksgiving break. No circumstances. Take it early. My flight changed, all that. None of that is going to be acceptable. 17th or 18th or 19th, plan on taking the quote final one of those days. All right. Now, so that's an extra day in case some people want to be sick the day or two before the 20th, right? Before breaks. So that's an important change. All right. So make your departure plans accordingly. Then after break, we are resuming online. The instructions I have received is to hold class in the normally scheduled time. So Monday, Wednesday, Friday, our same time slot, 9 to 9:50. 9 to 9:50 Central Time. I know some of you are going to other time zones. Back in the spring, when we basically closed down NC classes after spring break, I had one guy in Hawaii and one guy in Italy, right? And sometimes they were in the same sessions, 12 hours apart, right? So anyway, 9 to 9:50 Eastern Standard Time is when we're going to have this class, unless I hear otherwise, okay? I know other teachers may be doing something different and everything. That's their prerogative. Now, one thing I did do is, instead of 3 class meetings a week, sometimes I would put like a Friday one. I would pre-record the Friday one. Okay? And I would do that maybe on Thursday. Pre-record Friday's class. That way you can be flexed if you want to do something the weekend at home. It allows me flexibility too, but I don't care. Friday's a work day, right? So the Friday one maybe I'll pre-record, and then on Monday, during the COVID thing in last spring, I held Spark sessions. Right? I held Spark sessions right online. I sent out an invite to everybody, all of my students. Right? And anyone who needed help in their class, you tuned in, and I took questions one at a time from all over. And again, it was really cool. One help session, I had the guy from Hawaii, and I had the guy from Italy in the same call. Right? So my access to me does not disappear after Thanksgiving break. All right, I am very concerned about the success of every single student, and anyone who is struggling, anyone who wants to do better. I'm there to help you. Now, tutoring can only do so much of that. We've been through that before, right? Tutoring is part of that. I can help you solve problems and so forth, but the bigger issue is usually graphite to paper. Are you doing the work, right? Also, when you go home in your home environment, it can just be harder to concentrate, right? You might have siblings there. You might have a difficult home situation. You might, okay? I pray you don't, but I know some students do, right? You might have a situation that's even emotionally troublesome, stressful, so forth, right? I've had students already say, I'm coming back to campus because I don't want to be home for a month and a half. I don't want to be home from the middle of November until the second week of January, right? Or whatever. By the way, my understanding is, in anything you hear from student development, anything you hear from Dr. Mountjoy supplants anything I said. Don't say, Mr. Miller said. My understanding right now is that you can come back to campus for those last 2 weeks. That's my understanding, right? And many students are. My understanding also is that classes will be online during those 2 weeks. They're not going to allow NC classes. That's my understanding. I heard that just yesterday in a faculty meeting. Okay, from the president, by the way, of the college. But all that may change. You know how this works, right? All that may change. So anyway, if you were to come back to campus, maybe you have your sport or whatever that's still going to be going on. You may have to come back to campus. I still want to do my part in helping you succeed in here. Right? I want to be available, in person. Let's mask up and go to a whiteboard somewhere, right? Or if you want to do something online, online's a little harder. Unless I have this whiteboard here where you can see the problem worked out. It's a little harder with math, right? But we're going to work something out. We did before, and we're much better prepared now to handle this as a campus than we were back in March. Right? And I know I'm better prepared as an instructor, but I'm still learning. Right? So any questions on that? All right. I just want to get that going. Okay. So this is a very good section. The next 3 sections, and especially where we start today, we're going to be going through a 6-step process today. Right? This is another deeper kind of problem that you're going to have to work examples with. Graphite to paper, there's no substitute whatsoever for graphite to paper. We're going to be working 3 problems of this type. Some of them are going to be a little involved. And all of the things we said were essential skills before, if you did bad on the first test, bone up on those skills or they're going to come back to haunt you in these problems here because they all converge here. They all converge on this. All right. What we have, you remember from last time, was we have, back up here, a rational function is what we're talking about. And by rational function, we mean a ratio, right? Ratio of 2 polynomials. One polynomial divided by another. The degree of the numerator is n. The degree of the denominator is m. We call the polynomial in the numerator p. We call the polynomial in the denominator q. And those are the terms the book uses. Okay? So I'm going to try to stay as consistent with the book as possible. But one thing I'm going to do different than the book, I will make it known to you. Today, okay, we did this last time, went through these. 6-step process to graph rational functions. Now, the book uses 7 steps. I skipped the first step that they do. I used to teach it. I got slides for it. But it almost never applies. It almost never helps you. Right? And what it is to check for symmetry. And certainly you can do that. You can check for symmetry. But it almost never helps people. It's almost none of these are symmetric with respect to the y-axis. And so I skip it. That's the one difference I do from the book. All right? We're going to go through 6-step process to graph rational functions. And this is like a nice little intro example. It's a little harder, though, than what we did here. It's a little harder than these, right? Because you really cannot use transformations. How have we graphed functions so far? We've done transformations. You do a plan. You find a function that is most similar to it in the library of functions, and you apply transformations to that one to get the one that you want to graph, and then you apply those same transformations to the graph. That's been our procedure up to now. That doesn't really work here. I'll tell you something else that doesn't work right off the bat, right out of the block. People who don't study this, people who are behind on this, what they try on the exam is to plot points. You will get it wrong, very wrong, every time by plotting points. These defy plotting points. Although, they defy plotting points as a primary technique. They defy plotting points as your first technique. We are going to plot points in step 5. We are going to plot points, but we're going to plot points strategically. Right? Because what happens when people plot points? When people plot points, they do this. Oh, they plug in, got this point, they got this point, they got that point, they got that point, and then that point. Right? And what do people do? They play connect the dots. That's how people graph by plotting points. And for simple functions, that works. For these, but we are going to plot points in one part of the problem in a strategic way. We'll get there in a minute, in step 5. All right? So, notice that this top function is p of x, and it has degree n, which is 1. Degree 1, right? The bottom function is q of x, and that has degree m, which is 2. You're going to need those in the problem. Basically, if something has a name, you're going to use it. So if it calls it n and m, right? You know your p and q. You know you're going to use that terminology, right? So Find the y-intercept. Step 1, find the y-intercept if there is one. How do you find the y-intercept of any function in the universe? Plug in 0, right? So you plug in 0. In fact, I'm even going to emphasize it. People screw this up. I don't want you to screw this up. Right? Make that bold. And we will make it red. Right? Impossible to miss that one, right? Plug in 0. So f of 0 is 0 plus 4 on the top, 0 squared minus 4 on the bottom. Oh, by the way, those 4s don't cancel. You see this on tests. You go, you see. Those don't cancel. You can only cancel factors. Something that you factored off the top, something that's factored in the bottom, you can cancel those. You cannot cancel these. These are terms, okay? But you see that this equals 4 on the top minus 4 on the bottom. That is minus 1. So the y-intercept, and there may not be one. Sometimes there's not a y-intercept. The y-intercept here is minus 1. Now what you're going to do, is you're going to, over here, collect your evidence. Anything you find here, you're going to put on the graph here. So your graph is like your evidence blocker, you know, CSI, right? You're going to be collecting evidence about the graph, and you're going to be putting it on the graph immediately. Right? So number 2, find the horizontal, the horizontal intercept, the x-intercept. Oh, by the way, these steps have a logic to them. You're going to see there's intercepts, asymptotes, and then 2 other steps, okay? Intercepts first. X-intercept. How do you find the x-intercept in any function in the universe? You solve the function equal to 0. Right? And so that is, you're going to do x plus 4, f of x is, x squared minus 4, right? And you set that equal to 0. Now, solve that. Here is a very simple tool to solve these. Ready? A fraction, that's a fraction, right? That's a rational function. A fraction equals 0 when its numerator is 0 and the denominator is not. A fraction equals 0 when the numerator equals 0 and the denominator is not. Okay? We're going to get to what happens when the denominator is 0 as well. We're going to get to that. So we're going to do, this boils down to solving the top p of x equal 0, which is x plus 4 equals 0. So to solve that rational function equal to 0, I take the numerator, and I'm going to solve that equal to 0. And that gives me a very simple, straightforward x equal minus 4. This is the x-intercept. Up here's the y-intercept, right? So we're going to do minus 4 right here. Okay? Find intercepts. That was an essential skill, and people mess this up. They mess this up. Don't mess it up. Questions? All right. Now, I went ahead. Here's the graph again over here, and I got those 2 intercepts there for you, right? So that's our evidence we have so far. We are going to find vertical asymptotes. Vertical asymptotes. Rational functions may have several vertical asymptotes. They may have none, by the way. Okay. They are of the form x equals c. Now, don't write this on your paper, but a vertical asymptote looks like that. That's of the form x equals some number, and let's make that 2 here, right? That is the format of a vertical asymptote. And there may be several of those. I'm going to erase that. Okay? Where and occur where the denominator equals 0. And I should say denominator equals 0 and yeah, and the numerator does not. So the vertical asymptotes are found by solving Q of x equals 0. In the last step, remember that was solving P of x equals 0. In the last step, we solved numerator equal to 0. In this step, we solved denominator equal to 0. Like I said, these steps have a kind of a flow to them. Right? So Q of x, here's our function up here on the top right. Q of x is x squared minus 4 equals 0. X squared minus 4 factors. So that's x plus 2, x minus 2 equal 0. And by the zero product rule, remember the first day of class? Very first day of class, very first slide. This gives you x plus 2 equals 0, x minus 2 equals 0. Those are our two vertical asymptotes. Yes, sir.
Take off negative from both sides.
Yeah. If you want to, in this case, if you wanted to do it this way, make that x squared equal 4, you would be sure when you take the square root, you don't get x equals 2. X equal plus or minus 2. If you want to do it that way, that's fine in this case. But if you have a more complicated expression, that doesn't work. This does. So like if that had a cross term, and if it was x squared minus 3x minus 4, you couldn't do that, but you could do this. But in this case, if you want to put the 4 on the other side and just do x equal plus or minus 2, that's a little shorter. That's a good point, Mike. So we have vertical asymptotes. Always denote vertical asymptotes on your graph. For that matter, check. Always denote all asymptotes on your graph. Vertical, horizontal, or there's even going to be slant asymptotes. Vertical, horizontal, and slant. Okay, so these go on your graph at -2 and at 2. Okay? Dashed lines. Even if these coincide with an axis, even if these are coincide with an axis, do those dashes right over the axis. That communicates to the reader, me, or somebody else, that you know there's an asymptote there. Right. So that's how you find vertical asymptotes. So you do y-intercept, x-intercepts, of which there may be more than one. Here, there's never going to be more than one y-intercept. Because if there was another y-intercept here, it wouldn't be a function. It would fail the horizontal, vertical line test. X-intercepts, there could be more than one, there could be none. There are some of these we're going to graph that have no vertical intercepts, no y-intercept, no x-intercept. Yeah. Well, in fact, we already seen one. This one right here, it has no x-intercepts, no y-intercepts. None of these do. See that? So you won't get all of them. But it could have more than one x-intercept. Right? It could have more than one vertical asymptote, which it does here. Horizontal asymptotes. This is a very important slide. And I'm going to refer back to this slide several times in the next week or so. So I'm going to call this the horizontal asymptote slide, since I'm a creative genius, right? Horizontal asymptotes. How to find them. Here it is very, very important that you practice. Because you're going to have to basically know this slide. And it involves, here's the key. Compare N and M. How do you find horizontal asymptotes? The first step is you compare N and M. N is the degree of the top. M is the degree of the bottom. So for horizontal asymptotes, first part, compare N and M. Now, you may remember here, N up top here is 1. M down here is 2. So right here, you're going to look in this center column. Ready? Is N less than M? Is N equal to M? Is N greater than M? Okay? And ignore this bottom part for now, okay? Ignore that for now. We're going to get to it. So I have N equals 1. M is 2. So N is less than M. That puts me in this category. Everyone see what we did so far? Compare N and M. N is less than M. That puts us in this category. Now, that means the horizontal asymptote will be the x-axis. You can memorize that if you want to. So memorizers, just memorize it and ignore me for the next 30 seconds. Those of you who want to understand, why is this the case? Because you remember, like with polynomial functions, the x term that has the highest power of x is the bully. It pushes around all the rest of the parts of that equation. So the x term that has the highest power is the bully. It's going to grow fastest for even slightly larger powers of x. So here we see that the larger power is in the denominator. When n is less than m, that means the bottom has a bigger power. That means for even slightly larger values of x, the bottom is going to grow much, 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 much faster than the top. Right? It's going to grow according to this x squared, where the numerator grows according to x. Right? So the bottom is going to get very, very big, and the top is going to stay relatively small compared to the bottom. So something small divided by something big is small. Right? A small number divided by a big number is a small number, right? 2 divided by 1,000 is a small number. So when x gets a little bit big, this bottom is going to explode. The top is going to stay relatively small. The ratio of the two is 0. Will approach 0, I should say. The ratio of the top to the bottom will approach 0. Because you have a small top, a big bottom. And so 0, y equals 0, is the x-axis. That's why the x-axis is the horizontal asymptote when n is less than m. Because the bottom grows much, much faster. All right, we're going to get to now, suppose that the top grew faster. Right here. If there were, don't change your paper, if there were a cube right here, the top would have a higher degree. You'd be in this case here. That means the top is going to grow much faster than the bottom. So you're going to have a big number divided by a small number. So a big number divided by a small number is a big number. 10,000 divided by 2 is a big number. And so there will be no horizontal asymptote in that case. All right. We're going to get to an example of that. So in this case, what I want everyone to see, in this case, is that n is less than m, the x-axis, y equals 0, is the horizontal asymptote. All right? Now this is interesting. Oh, look at this. We're not going to need this time, okay? But we're not going to need this time. But what I want you to take away from this slide now, we're going to come back to this slide, right? What I want you to get from this slide now is, unlike a vertical asymptote was created how? The denominator is 0, right? Denominator can never be 0. Whatever number that makes that vertical, if this is x equal 2, that means if you plug 2 into the function, you get 0 on the bottom. So 2 isn't even in the domain. 2 is not even in the domain of the function if you have a vertical asymptote. So vertical asymptotes, I was joking around the other day, they're like electrified fences, right? The graph never, ever touches a vertical asymptote. Never touches. But horizontal asymptotes, it says this on the slide, horizontal asymptotes, the graph can touch horizontal asymptotes for relatively small values of x. So let me translate that. Horizontal asymptotes are only horizontal asymptotes in the tails. Okay? For relatively small numbers, the graph can cross horizontal asymptotes because it doesn't create a 0 in the denominator. That's why. So the horizontal asymptote, this is the value to which the graph eventually settles down to. It eventually does, out in the tails. Now, usually it doesn't take that long. For the ones we're going to do, it doesn't take that long for it to settle down near. It's going to approach the horizontal asymptote for reasonably small values of x. But it could, and often does, cross a horizontal asymptote for small values, right? Now, in fact, right here, what is our horizontal asymptote? The x-axis, right? But we have an x-intercept, right? We have an x-intercept at -4. So even in this problem, the graph is going to cross the horizontal asymptote. Now let's go here. That's what I want you to take off the slide now. Now, we're going to come back to this slide. So now we have, since n is less than m, the x-axis is the horizontal asymptote. So that means you have this, x-axis. Always dash that in. And you notice that right here, we have an x-intercept on the x-axis, obviously. Where else would you have an x-intercept? That x-intercept is on the horizontal asymptote. And that can happen. It happens here, right? Does the graph cross the horizontal asymptote? Yes. At x equal -4. All right? So I want to stress vertical asymptotes, they are electrified fences. Graphs never touch them. Horizontal asymptotes, sometimes they're not touched either. Sometimes they're not touched either. But sometimes they are. In this case, it was. So we're done with the first 4. The first 2 are intercepts. Y and x intercept. The next 2 are asymptotes, vertical and horizontal asymptotes. Step 5 is where we're going to plot some points. Now, very important. What I have written here, you're going, that's a lot to read. The other slide was a lot to read. Believe me, it's less than it's in the book. Very important. We are going to plot points, but not just any old crazy points. We're not going to plot just any old crazy point. What do we have now in our graph? We have x-intercepts and vertical asymptotes. Hear me very carefully. The only places that the graph could change signs, that the function could change signs, is at an x-intercept or a vertical asymptote. We'll say that again. The only points at which the function could change signs. I just freaked out somebody's mother at home. The only places the function could change signs is at vertical asymptotes or an x-intercept. Now, don't mess up your graph here, but let me show you what I mean. For example, at this x-intercept, we know there's different behaviors at that intercept, right? It could go like this. It could change signs, right? Or it could do this and bounce. So it may change signs, it may not. In any case, it's going to touch the x-axis there. It's going to touch the x-axis there. It just may not change signs. All right? All right? The second place it could change signs is at the vertical asymptotes. So it could go to infinity in one direction, say negative infinity here, and it could go to positive infinity on the other side. That can happen. So it could change signs there. It's almost like it goes down to negative infinity and wraps back around somehow, right? Okay? So it could change signs there. Now, it also is possible it goes to negative infinity on one side, negative infinity on the other. You can do that too. All right? Okay. So, key number one. The only places at which the function can change signs is at a horizontal intercept, x-intercept, or a vertical asymptote. That's it. The function does not change signs in any other place. That's going to be valuable information. So what we're going to do now, yes, sir. Oh, yeah. Good idea. Let me repeat that. The only places, and it's written here in the stuff, the only places at which the function, a rational function, can change signs are at x-intercepts or vertical asymptotes. That's it. It cannot change signs anywhere else. What does that mean? For example, don't write this on your paper, but you see you have a x-intercept at -4, right? All the way out here, from -4 all the way to negative infinity, the function cannot change signs. Why? Because there's no other x-intercepts and there's no other vertical asymptotes out here. Out here, there's no more x-intercepts, no more vertical asymptotes. It can't change signs. Right? Similarly, in between these, in between those two asymptotes, there's no other vertical asymptotes. There's no other x-intercepts. So in between those vertical asymptotes, it has the same sign. Okay. And at those asymptotes, we know it goes to either plus infinity or minus infinity. We know that. By the way, we also know what sign it is. What sign does the function have between these two? Negative. So that means this graph, and I'm going to erase this and do it again, this graph has to have that shape there. That's the only possible shape it could have, because it can't do this. Because if it did that, it would have another x-intercept. And it doesn't have it, right? And then similarly, on this side of that intercept, it cannot change signs out there. So it cannot change signs between, I'll erase all that green. I just put. Right? It cannot change signs between x-intercepts and vertical asymptotes. It can only change signs at those. And it may not change signs at the vertical asymptote or at the x-intercept. So right here, we're going to plot points strategically. And what we're going to do is we're going to plot points in each of these intervals. I'm going to plot a point out here. I'm going to plot a point in there. I'm going to plot a point between these two, which I already did. That's the -1, right? Then I'm going to plot a point out here. And once I plot the point, guess what? That function has to be that sign for the rest of that interval. All right? So your goals here are to determine whether the graph changes signs at x-intercepts, whether the graph changes signs or is above or below the horizontal axis or oblique asymptote, if there is one. All right? Whether the graph goes to positive or negative infinity at the vertical asymptotes. I told you there's a lot involved in these, right? I warned you going in, right? Now, so here's how we're going to do that. You make yourself a little chart like you have here at the bottom right. In the far left column, you're going to put in order every x-intercept or vertical asymptote with some space between them. So, for example, x-intercept, I have one at -4. The next one I encounter is a vertical asymptote at -2 and a vertical asymptote at 2. So leave some space there. So you put them in order here. Now what you're going to do is you're going to pick one point. What you've done with those 3 points in purple, you have divided the entire x-axis into 4 intervals. -4 to -infinity, -4 to -2, -2 to 2, and then 2 to infinity. You pick one point in each interval. So, for example, I'm going to pick one point out here somewhere to the left of -4. I'm going to pick, say, -5. Then I'm going to pick a point between -4 and -2. -3, right? Then I'm going to pick a point between -2 and 2. The good news is we already have a point there, right? We did the y-intercept. So we're going to pick 0. Because we already did that one. We know the answer is -1. And then I'm going to pick a point beyond 2. Beyond 2. And I'm going to pick a point at 3. So you see what I did? These 3 points in purple, they divide the horizontal axis into 3 intervals. Excuse me, 4 intervals. Those 3 points divided into 4 intervals. And so we picked one point in each interval, these green numbers. One of them we already did. Now what we're going to do in the third column is we're going to evaluate our function. And all we're interested in is the sign. I have the sign. Okay? We're just interested in the sign. If you want to get the exact value, that's okay. So here, we're going to have -5 plus 4 divided by -5 squared minus 4. You plug that in, do some evaluating. The top is -1. The bottom is 25 minus 4. 25 minus 4 is 21. Well, a student will observe that is negative. So I'm going to go up here. Watch what we do. We're going to take this at -5. It's -121. So that's like right there. Right below the x-axis. Right? Now we do that again for these other points. For -3. -3 plus 4 on the top. -3 minus 4 in the bottom. What happens? We have a +1 in top divided by 9 minus 4 5 in the bottom, that is positive. So we see it changes signs at that x-intercept. It doesn't always change signs at x-intercepts. But here we have 1/5. So we go up here to -3, and we plot a point at 1/5. So you see what happens at that point. It crosses. All right, so we're down here again. At 0, we have -1. So we already have that point on our graph. Then beyond 2, we're going to pick 3. And we're going to have 3 plus 4 in the top, 3 squared minus 4 in the bottom. That's 7 on top, 9 minus 4, 5 on the bottom, which is positive. Which is positive. So we go up here, 7/5 at 3. 7/5 is about right here. Right? Okay. We just have a couple minutes left, but we're done basically. Let me show you what you do now. Any questions on that? So we go to the next page. All that's on there, right? All those points are on this graph. What we do is now we play connect the dots. You remember? So we did plot points here, but we plotted them strategically. And now we're going to connect the dots, but we're not going to do this. We're not going to do it like, we're not going to do that. Why? That doesn't respect our asymptotes and stuff. All right? So we know that the x-axis is a horizontal asymptote. So we know out here, it's negative here. It's got to be negative all the way out here. So the graph is going to be very close to the x-axis. It's going to go through this point. It's going to cross the x-axis here. It's going to go here through that point at 3. And then it's got to shoot up. Right? It's got to go up to positive infinity. It can't go down. Does everyone understand why it can't go down? Because if it did go down, it would be another x-intercept. And we don't have one. You see, the fact that we account for all our x-intercepts is very important. Almost out of time here, so let me. Here we already mentioned, does this come from the top or from the bottom? Well, in this section, it's negative. So this must come from negative infinity, cross through 1, and go back down. Has to do that. Because it's negative for that whole interval. And last, in this interval out here, there's only one thing it can do. It's got to be positive the whole time, right? So it's got to come down from positive infinity, go through our point, and then make an asymptote there. It can't cross like this. Because if it did, there would be another x-intercept. All right, we're out of time. We'll pick up on this on Friday, do a little review of that problem. In the meantime, this homework. This homework will be similar to what we just did. I'll give you a clue. It has a different horizontal asymptote. All right? See ya.